Okay, we are now ready for chapter 14, which is all about trigonometric identities. First of all, identities are just, you know them as properties, laws, things that are always true. An identity is usually an expression that equals another expression, and we call that an identity. And in trig, all these expressions are going to have trig ratios in them. And we're going to prove many of them, the ones that are used most often, and then other identities that aren't used that often, you're just going to prove them as exercises. So the first batch of identities is called the Pythagorean identities because they're all based on the well-known identity known as Pythagorean theorem, a squared plus b squared equals c squared. Now in the trig chapters, your textbook likes to call the legs and the hypotenuse differently. So they use u for the, if this is theta, they use u for the adjacent side, v for the opposite side, and r for the hypotenuse, I assume, because that would be the hypotenuse of a unit circle, for example. So to derive our first identity, we use u, v, and r as the sides and just plug them into the Pythagorean theorem. And then we divide both sides by r squared. And then I rewrite each fraction like this. And then I take note that u over r is adjacent over hypotenuse, and that's the same thing as cosine. And since the whole thing is squared, I can put the squared here. And v over r is sine. And there's our first Pythagorean identity. Cosine squared of theta plus sine squared of theta equals 1. Okay, there are two more Pythagorean identities, and they're both based on this. So I'm going to take this identity and I'm going to divide both sides by sine squared. Okay, and then since cosine over sine is also known as cotangent, I can replace this with cotangent squared. And since 1 over sine is the same thing as cosecant, I can change this to cosecant squared, and I have my second identity. And then for the third, I go back to the original identity. And this time I divide by cosine squared. Oops, that should be equals. I think you know where I'm going with this. I'm going to replace this with tangent squared and replace this with secant squared. And there's my third identity. So make sure you commit these three to memory, because when you're proving other identities and you need to use these identities in order to make it to the next step, you don't want to have to flip through your library of identities. You want to just know it and do that step and move on to the next step. Okay, so how do we use these identities? We would use them in a situation like this, when we're trying to prove another identity. This identity. We want to prove that cotangent of x plus tangent of x equals the product cosecant x secant x. Now when we're done, this will be a proven identity that you can use anytime. But in the examples I'm going to show, these are not identities that I recommend committing to memory, because you're probably never going to see this identity again, because it's a very specific situation. But these three identities, you're gonna see these situations all the time. That's why these need to be committed to memory. Okay, so when we prove identities, we normally pick a left side or a right side, and we attempt to transform that side that we pick into the other side. How do we pick? Usually it's easier if you pick the more complicated side and turn it into the other side. Just as you have any expression in algebra, it's much easier to take that expression, simplify things by combining like terms, etc., to turn it into the expression that has only one term in it, for example. It'd be much harder to take one term and expand it to make it look like something that has multiple terms. So since this has two terms and the right side only has one, I'm going to start with the left side. So proof, I'm going to start with cotangent of x plus tangent of x. And rule of thumb is when you have trigonometric ratios that aren't in terms of cosine and sine, we turn them into cosine and sine, because those are our building blocks. So I'm going to change cotangent of x to cosine x over sine of x, and tangent of x, that's not squared, into sine of x over cosine x. And now I just start simplifying algebraically. So I try to get common denominator. Sine, cosine. Sine times cosine would be my common denominator. So I'm going to multiply this fraction by cosine x over cosine x. And this fraction will multiply by sine x over sine x. Okay. I have my common denominator. I added the fractions by adding the numerators. And then, conveniently, this numerator is one of our identities. Cosine x plus sine of x, cosine squared of x plus sine squared of x is 1. How convenient. So I get this, which I can write as 1 over sine times 1 over cosine, which I can then in turn write as cosecant x times secant x. And if I'm being really, really proper, I'd say therefore cotangent of x plus tan of x equals that, and it's proven. But you don't have to do that last step. You can just end it here, because if you're presenting this to me or someone else, I can see that you started with this and that it equals this, and I know that that's what you're trying to prove. So QED, it's proven. Okay, second example. We're going to prove that sine of x over 1 plus cosine of x equals 1 minus cosine x over sine of x. Okay, again, remember this is something not proven yet, so I cannot take this equation, since it isn't proven yet, and multiply something on both sides of it, because then I'd be assuming that it's true. I know that the book is not going to give you things that aren't true to prove, but this is the practice. This is the exercise. So I'm going to pick the left side to work on because the denominator has two terms in it. So what I'm going to do is multiply the top and the bottom by something convenient that leads me in the direction of one of those Pythagorean identities. And you need a little creativity here, and with experience, it'll be like it'll come to you in a split second after you do this a couple times. I'm going to multiply by 1 minus cosine x. And if you look at the denominator, you'll see why I did that. It's a difference of squares, 1 minus cosine squared, and 1 minus cosine squared is a version of our first Pythagorean identity, this one. If I subtract cosine squared on both sides, then you'll see what it equals. So 1 minus cosine squared is sine squared. And now I can cancel. And QED, I'm done. Okay, next one. Cosecant of x times cosine squared of x plus sine of x equals cosecant of x. So obviously the left side is more complicated, so I'm starting with that. Okay, cosecant is not in terms of sine and cosine, so I'll change that to 1 over sine. And put cosecant squared on top. And I'd like to add these two terms, so I'm going to get common denominator. Oh, so conveniently I get cosine squared plus sine squared, and by now I know easily that that's 1. So 1 over sine x is cosecant of x, QED, done. Okay, so remember, when you're proving identities, choose the more complicated side. If things are not in terms of sine and cosine, change them in sine and cosine, and then just manipulate it until you get the other side. And in the first exercise, you're trying to create Pythagorean identities. So you want to create expressions that you know equal 1. Or you want to create expressions that have 1 minus cosine squared, or 1 minus sine squared, or 1 plus tangent squared, or cotangent squared plus 1, because you know what those expressions equal. Okay, good luck.